It all began with a documentary that claimed the astronauts never ever landed on the moon, that the whole event was faked by the Americans, filmed on a movie set.
There is a lot we don't know yet about the moon, especially the dark side of the satellite. Then there is also the information kept hidden by the authorities about this little-known side of the moon. However, in this video, we bring you details of how a Soviet-era cosmonaut breaks the silence about the secret mission to the far side of the moon. The far side of the moon is the lunar hemisphere that always faces away from Earth, opposite to the near side, because of synchronous rotation in the moon's orbit. Compared to the near side, the far side's terrain is rugged, with a multitude of impact craters and relatively few flat and dark lunar maria or seas, giving it an appearance closer to other barren places in the solar system, such as Mercury and Callisto. It has one of the largest craters in the solar system, the South Pole Aitken Basin. The hemisphere has sometimes been called the dark side of the moon, where dark means unknown instead of lacking sunlight. Each side of the moon experiences 2 weeks of sunlight, while the opposite side experiences 2 weeks of night. About 18% of the far side is occasionally visible from Earth due to libration. The remaining 82% remained unobserved until 1959, when it was photographed by the Soviet Luna 3 space probe. The Soviet Academy of Sciences published the first atlas of the far side in 1960. The Apollo 8 astronauts were the first humans to see the far side in person when they orbited the moon in 1968. All crewed and uncrewed soft landings had taken place on the near side of the moon until January 3, 2019, when the Chang'e 4 spacecraft made the first landing on the far side. Astronomers have suggested installing a large radio telescope on the far side, where the moon would shield it from possible radio interference from Earth. Due to tidal locking, inhabitants of Earth will never be able to see this part of our satellite. Tidal forces from Earth have slowed down the moon's rotation to the point where it always faces Earth, a phenomenon called tidal locking. The other face, most of which is never visible from Earth, is therefore called the far side of the moon. Over time, some crescent-shaped edges of the far side can be seen due to libration. In total, 59% of the moon's surface is visible from Earth at one time or another. Useful observation of parts of the far side occasionally visible from Earth is difficult because they cannot be observed full on. A common misconception is that the moon does not rotate on its axis. If that were so, we would be able to see all sides of it over time. Instead, its rotation period matches its orbital period, meaning it turns around once for every orbit it makes. In Earth terms, its day and year have equal length. That is, about 29.5 Earth days. In June 2009, Lunar Reconnaissance Orbiter, or LRO, launched from Kennedy Space Center in Florida. The Lunar Reconnaissance Orbiter, or LRO, is a NASA robotic spacecraft that has been orbiting the moon since 2009, collecting high-resolution images and data that are essential for planning future human and robotic missions to the lunar surface. LRO has achieved many remarkable feats and discoveries that have changed our view of the moon and its history. LRO has created a 3D map of the moon's surface at 100-meter resolution and 98.2% coverage, excluding polar areas in deep shadow. This map reveals the moon's topography, geology, temperature, and radiation in unprecedented detail, and helps identify safe landing sites and potential resources for future explorers. LRO has taken extremely high-resolution photographs of landing sites of several older lunar landers and impact vehicles, such as those from all of the Apollo landing missions, the Surveyor 3 probe, and the Soviet Luna and Lunokhod missions. These images show the tracks, flags, instruments, and even footprints left by the previous visitors, and provide valuable information on how the lunar environment affects human-made materials over time. LRO has detected laser signals bounced off the moon by Earth-based stations, using its Lunar Orbiter Laser Altimeter, or LOLA instrument. LOLA measures the distance between LRO and the lunar surface by firing laser pulses and timing their return. It can also locate retroreflectors, which are devices that reflect light back to its source. There are 5 retroreflectors on the Moon, 3 left by Apollo astronauts, 1 by the French-built Lunokhod 2 rover, and 1 by Lunokhod 1. In 2010, LRO found the long-lost Lunokhod 1 rover and its retroreflector, which had stopped responding in 1971. LRO also measured the distance to Lunokhod 1 with an accuracy of about 1 centimeter, which is remarkable considering that it is about 400,000 kilometers away from Earth. LRO has discovered evidence of water ice on the Moon using its Lyman Alpha Mapping Project, or LAMP, and Lunar Exploration Neutron Detector, or LEND instruments. LAMP detects ultraviolet light reflected by the lunar surface, while LEND measures neutrons emitted by the lunar soil. Both instruments can sense the presence of hydrogen atoms, which are a sign of water molecules. LRO found that some permanently shadowed craters near the lunar poles contain water ice deposits that could be used as a resource for future missions. LRO also detected water vapor released by meteoroid impacts on the lunar surface. LRO has studied the Moon's volcanic history, using its Diviner Lunar Radiometer Experiment, or DLRE, and Lunar Reconnaissance Orbiter Camera, or LROC instruments. DLRE measures the thermal emission of the lunar surface, while LROC captures visible and near-infrared images of the lunar terrain. Both instruments can reveal features related to volcanic activity, such as lava flows, pyroclastic deposits, rills, domes, and vents. LRO found that some of these features are much younger than previously thought, suggesting that the Moon was volcanically active until relatively recently in geological terms. LRO also discovered a new type of volcanic landform on the Moon, irregular mare patches, or IMPs, which are small areas of smooth and dark material that may have formed from explosive eruptions or lava fountains. LRO has investigated the Moon's magnetic field, using its cosmic ray telescope for the effects of radiation, or crater instrument. Crater measures the energy and flux of cosmic rays and solar energetic particles that reach the lunar surface. These particles can affect the health of astronauts and electronics on future missions. Crater also detects anomalies in the local magnetic field caused by magnetized rocks on or below the lunar surface. These rocks may have formed when the Moon had a global magnetic field in its early history, or when it was impacted by meteoroids that generated transient magnetic fields. Some of these rocks create mini magnetospheres that deflect some of the incoming particles and create swirl patterns on the surface. China's Chang'e 4 mission is the first and only human mission to land and explore the far side of the Moon. It consists of a lander, a rover named Yutu-2, and a relay satellite named Queqiao. The mission was launched on December 8, 2018, and entered lunar orbit on December 12, 2018. The lander and rover touched down on January 3, 2019, in the von Karman crater, which is located in the South Pole Aitken Basin. The South Pole Aitken Basin is the largest and oldest impact crater in the solar system, measuring about 2,500 kilometers in diameter and 13 kilometers in depth. It is believed to have formed about 4 billion years ago when a large asteroid hit the Moon. The impact may have exposed some of the Moon's mantle material, which could provide clues about the Moon's origin and evolution. The Chang'e 4 mission has 9 scientific instruments on board. 4 are on the lander, a landing camera or LCAM, a terrain camera or TCAM, a low-frequency radio spectrometer, and a lunar lander neutrons and dosimetry LND provided by Germany. 4 are on the rover, a panoramic camera or PCM, a visible and near-infrared imaging spectrometer or VNE, a lunar penetrating radar or LPR, and an advanced small analyzer for neutrals or ASAN provided by Sweden. The instrument on the relay satellite is the Netherlands-China Low-Frequency Explorer NCL. The scientific objectives of the Chang'e 4 mission are: 1. To perform low-frequency radio-astronomical observations using LFRS and NCLE. The far side of the Moon is an ideal place for radio astronomy because it is shielded from the radio interference from the Earth and the Sun. LFRS can detect radio waves in the frequency range of 1 to 30 MHz, while NCLE can detect radio waves in the frequency range of 80 kHz to 80 MHz. These instruments can study the cosmic dawn, which is the period when the first stars and galaxies formed in the early universe. 2. To investigate the geomorphology, mineral composition, and shallow subsurface structure of the landing and roving sites using LCAM, TCM, PCM, VNIS, and LPR. These instruments can capture high-resolution images and spectra of the lunar surface and probe up to 100 meters below it. They can identify different types of rocks and minerals, such as basalt, olivine, pyroxene, plagioclase, ilmenite, and spinel. They can also reveal features related to volcanic activity, such as lava flows, pyroclastic deposits, rills, domes, and vents. 3. To detect the Earth-Moon space environment at the lunar far side using LND and ASAN. These instruments can measure the radiation levels and neutral atoms on the lunar surface. They can help understand how cosmic rays and solar wind interact with the lunar soil and atmosphere. The Chang'e 4 mission has made several discoveries and achievements since its landing. Some of them are: it found evidence of water ice in permanently shadowed craters near the lunar poles using VNIS. Water ice is a precious resource for future lunar exploration and colonization, as it can be used for drinking, farming, and producing oxygen and fuel. But how did Chang'e 4 find water ice on the moon? The answer lies in one of the scientific instruments on board the Yutu-2 rover, the Visible and Near-Infrared Imaging Spectrometer, VNIS. VNIS is a device that can measure the reflected light from the lunar surface and analyze its spectrum. Different types of materials have different spectral signatures, which can reveal their chemical composition. VNIS can detect minerals such as basalt, olivine, pyroxene, plagioclase, ilmenite, and spinel, as well as organic molecules and water molecules. VNIS works by scanning the lunar terrain with a laser beam and collecting the reflected light with a telescope. The light is then split into different wavelengths by a grating and detected by a sensor. The sensor records the intensity of each wavelength and converts it into a spectrum. The spectrum is then compared with a database of known spectra to identify the materials present on the lunar surface. Using VNIS, Chang'e 4 detected water ice in some permanently shadowed craters near the lunar poles. These craters are so deep and cold that they never receive direct sunlight, and thus can preserve water ice for billions of years. The water ice may have originated from comets or asteroids that crashed into the moon, or from the solar wind that implanted hydrogen atoms into the lunar soil. The Chang'e 4 mission also detected low-frequency radio waves from the early universe using LFRS. This is a breakthrough in radio astronomy that could shed light on how matter evolved after the Big Bang. It also measured radiation levels on the lunar surface using LND. The results showed that radiation exposure on the moon is about 200 times higher than on Earth. This has implications for astronaut health and safety. The Chang'e 4 mission also grew plants in a sealed container using a biosphere experiment. The experiment was designed to test the feasibility of creating a mini biosphere, an artificial, self-sustaining environment on the moon. The biosphere was a small, sealed container that contained soil, water, air, nutrients, and seeds of cotton, potato, and thale cress, a flowering plant. It also had yeast and fruit fly eggs to form a simple food chain. The container was equipped with a temperature control system, a water supply system, and a camera to monitor the growth of the plants. The experiment was launched on December 8, 2022, along with the Chang'e 4 lander and rover. It reached the moon on January 3, 2023, and landed in the von Karman crater, a large impact basin in the South Pole Aitken Basin. The biosphere was activated after the landing, and soon after, the cotton seeds began to sprout. On January 15, 2023, the Chinese National Space Administration announced that they had received images of a cotton seedling growing in the container. This was a remarkable achievement, as it marked the first time that any biological matter had grown on the moon. The cotton plant was not alone in its lunar adventure. The potato and thale cress seeds also germinated and grew leaves. The yeast and fruit flies also showed signs of life. The experiment demonstrated that plants could grow and photosynthesize in the low-gravity and harsh environment of the moon. It also showed that a simple ecosystem could be maintained in a closed space with limited resources. The experiment was not meant to last long, however. The lunar night, which lasts for about 2 weeks, brought extremely low temperatures that killed the plants and other organisms. The container was not designed to withstand such conditions, and it did not have a heating system or a battery to keep it warm. The experiment ended on January 12, 2023, when the biosphere entered its first lunar night. Despite its short duration, the experiment was a huge success for China and for space exploration. It opened up new possibilities for future missions that aim to establish long-term human habitation on the Moon or other planets. The Chang'e 4 mission also discovered a new type of volcanic rock on the Moon. The rover used a spectrometer to analyze the reflected light from different minerals on the surface, and found 2 patches of rocks that were rich in olivine and low-calcium pyroxene. These minerals are not common in the lunar crust, but they are expected to be abundant in the lunar mantle, which is the layer below the crust. The lunar mantle is largely inaccessible to direct observation, as it lies beneath a thick layer of basaltic lava that covers most of the Moon. However, some scientists have proposed that large impact events, such as the one that created the South Pole Aitken Basin, where Chang'e 4 landed, could have excavated some mantle material and brought it to the surface. The new type of volcanic rock found by Yutu-2 could be evidence of this process and could provide valuable clues about the origin and evolution of the Moon. The discovery of this new type of volcanic rock is also important for understanding the volcanic history of the Moon. Previous samples returned by the Apollo and Luna missions showed that most of the lunar volcanism occurred between 3.8 billion and 3 billion years ago, when large amounts of magma erupted and filled the basins on the near side. However, Chang'e 4 landed in a region that is thought to be much younger, with lava flows dating back to about 2 billion years ago. This suggests that the Moon was still volcanically active for much longer than previously thought, and that there might be regional variations in the timing and intensity of eruptions. The Chang'e 4 mission also explored more than 1 kilometer of lunar terrain using the Yutu-2 rover. The rover has set a record for being the longest operating rover on the Moon. The Soviet Union, however, holds the record for sending the first probe to take photos of the dark side of the Moon using the Luna 3 probe. The Luna 3 probe was a groundbreaking mission that revealed the hidden face of the Moon for the first time in human history. It was a remarkable feat of Soviet engineering and science and a milestone in the exploration of our nearest celestial neighbor. The Luna 3 probe was launched on October 4, 1959, by a Proton K rocket from the Baikonur Cosmodrome. It was the 3rd Soviet spacecraft to reach the vicinity of the Moon after Luna 1 and Luna 2, which had flown past and impacted the lunar surface, respectively. The Luna 3 probe had a different objective: to fly around the Moon and photograph its far side, which had never been seen before. To achieve this goal, the Luna 3 probe had a unique design. It was a cylindrical canister with hemispherical ends and a wide flange near the top. It had several solar cells on its surface to provide electric power and shutters for thermal control. It also had 4 antennas for communication with Earth, and various scientific instruments such as micrometeoroid and cosmic ray detectors. The most important instrument, however, was the Yenisei 2 imaging system, which consisted of 2 cameras, a film processing unit, and a scanner. The Yenisei 2 imaging system was ingenious and innovative. It used 40 square frames of temperature-resistant, radiation-hardened film that were stored in a lead-lined cartridge. The film was originally from the U.S.'s Genitrix high-altitude reconnaissance balloons, which had been captured over Soviet airspace in the late 1950 S2. The cameras could take pictures with 2 different lenses, a 200 mm f5, 6 lens for wide-angle views, and a 500 mm f9, 5 lens for close-ups. The film processing unit could develop and dry the film automatically, using chemicals that were stored in sealed containers. The scanner could then scan the film frames with a cathode ray tube and transmit them as electric signals to Earth via radio waves. The Luna 3 probe reached the Moon on October 6, 1959, and performed a maneuver to enter an elliptical orbit around it. It then activated its cameras and took 29 pictures of the lunar far side, covering about 70% of its surface. The pictures were taken at distances ranging from 6,200 kilometers, or 3,900 miles, to 66,700 kilometers, or 41,400 miles from the Moon. The probe then processed and scanned the film frames and began to transmit them to Earth on October 7th. The transmission lasted until October 18th, with some interruptions due to technical difficulties and unfavorable positions of the probe and Earth. The pictures received by the Soviet operators were of poor quality due to various factors such as noise, distortion, interference, and low resolution. However, they were still recognizable as images of the Moon's far side, and they showed features that were radically different from those of the near side. The far side had much fewer maria than the near side, and much more rugged terrain, with numerous craters and mountains. The only two large maria visible were named Mare Moscoviense, or Sea of Moscow, and Mare Desiderii, or Sea of Desire, although the latter was later found to be composed of smaller features such as Mare Ingenii, or Sea of Cleverness, and several dark craters. The pictures sent by Luna 3 caused excitement and interest around the world, as they revealed a new aspect of our familiar companion in space. They also challenged some assumptions about the origin and evolution of the Moon, and raised new questions about its geology and history. The Soviet scientists published an atlas of the far side of the Moon in 1960, based on image processing techniques that improved the quality of the pictures. They also named many features on the far side, using mostly Russian names or names related to space exploration. Some of these names are still in use today, while others have been changed or replaced by international conventions. The Luna 3 mission lasted until October 22, 1959, when it lost contact with Earth due to a failure in its radio system. It decayed from orbit and re-entered Earth's atmosphere on April 29, 1960. The probe had accomplished its mission successfully, and had made history by unveiling the Moon's far side for the first time. It also demonstrated the Soviet Union's technological prowess and scientific curiosity, and paved the way for future lunar exploration by both robotic probes and human astronauts. Another of the Soviet Union's missions to the Moon is the Lunokhod 1 mission. It was the first time that a robotic rover was able to explore the surface of another world and send back valuable scientific data and images. The mission demonstrated the Soviet Union's technological prowess and scientific curiosity, and paved the way for future lunar exploration. The Lunokhod 1 rover was carried by the Luna 17 spacecraft, which was launched on November 10, 1970, by a Proton K rocket from the Baikonur Cosmodrome. After 2 course correction maneuvers, Luna 17 entered lunar orbit on November 15th and began to prepare for landing. On November 17th, at 3:47 UTC, Luna 17 softly touched down on the Mare Imbrium near the crater Leonid. The landing site was chosen for its flat terrain and favorable lighting conditions. About 4 hours after landing, the rover emerged from the spacecraft and deployed its solar panels and antennas. The rover was shaped like a tub with a large convex lid and had 8 independently powered wheels. It was equipped with 4 television cameras, an X-ray spectrometer, an X-ray telescope, cosmic ray detectors, and a laser retroreflector supplied by France. The rover also had special devices to test the lunar soil for density and mechanical properties. The rover was powered by batteries that were recharged by solar cells during the lunar day. During the lunar night, the rover would close its lid and use a polonium-210 radioisotope heater to keep warm. The rover was controlled remotely by operators in the Soviet Union, who received telemetry and images from the rover via a large parabolic antenna in Crimea. The operators could also send commands to the rover via a helical antenna on Luna 17. The communication delay between Earth and Moon was about 2.5 seconds, so the operators had to anticipate the rover's movements and avoid obstacles. The rover could also perform some autonomous actions, such as stopping when it detected a hazard or when it lost contact with Earth. The Lunokhod 1 mission lasted much longer than expected. The original plan was to operate the rover for 3 lunar days, about 3 Earth months, but the rover proved to be very resilient and reliable. It survived 11 lunar days, about 11 Earth months, and covered a total distance of 10.54 kilometers or 6.55 miles. During its journey, it transmitted more than 20,000 TV images, more than 200 TV panoramas, more than 500 soil tests, and more than 140 lunar soil samples by X-ray fluorescent spectrometer. It also measured the magnetic field of the moon, detected cosmic rays and solar wind particles, and reflected laser beams from Earth-based observatories. The Lunokhod 1 mission ended on September 14, 1971, when it lost contact with Earth due to a failure in its radio system. The last image sent by the rover showed its own shadow on the lunar surface. The rover remained silent until April 2010, when NASA's Lunar Reconnaissance Orbiter (LRO) located it using its high-resolution camera. The LRO also found the Luna 17 lander and its tracks on the moon.